In previous videos, we defined the Gaussian distribution or the normal distribution as this PDF. Looks like this bell curve. Well, with the Gaussian distribution for a single random variable. We also discussed random vectors, where every element of the vector is a random variable. Find the covariance matrix, covariance of a single random vector, and linear transformations of random vectors. So that was all in previous videos. So now that we've got all those ingredients, let's talk about the multivariate Gaussian distribution. That means its argument is a random vector made up again of random variables. Well, here is PDF, the probability density function of a Gaussian random vector. So this X here, the big X here is a random vector. Little x is also a vector, a realization of the random vector. And this C here is the covariance matrix. And this notation here means the determinant of it, which is a matrix. You got to know a little bit about matrix arithmetic and know what a determinant is. So anyway, that's what it is. That's the PDF of a multivariate Gaussian distribution. In the bivariate case, where it's only two random variables in your vectors, say x1 and x2, here's what that covariance matrix would look like. Take my word for it. Here's what the determinant would be. And you can break through the calculations up here and put it sort of into scalar form. You know, there's no matrices down here. Just the x1 and the x2 and their means. And now this rho is just a correlation coefficient between just those two random variables. This rho. Well, let's see. If they're uncorrelated, rho is 0. So this term goes away. And this middle term goes away. So you break up this exponent. This thing here, this whole middle term goes away. I'm kind of getting ahead of myself. That if they're uncorrelated, Gaussian random variables, then they're also independent. We can just go through this and the joint PDF of the two variables is can break up into individual PDFs for the individual random variables. That's if they are uncorrelated. Let me get back to this. We already did this before. For this top part is true for any random vector. If y, a random vector, is this linear function of another random vector x, you can calculate its mean and covariance from the mean and covariance of the x. But in the case of a Gaussian random vector, if x is Gaussian, y is also Gaussian. The nice thing about Gaussians, you do a linear operation on a Gaussian vector, you get another Gaussian. So we not only have these two, in the case of a Gaussian, we not only have the mean and covariance, we have the whole PDF, the whole joint PDF. And output, or the result, is also Gaussian. Yeah, if in the case of Gaussian, if they're uncorrelated, that does imply independence. Generally, in general, that was not true. I also want to introduce this concept of an air ellipse or even ellipsoid. If you've just got two random variables in that random vector, if you set the probability to a certain number, you, you know, you set this equal to a number, you are setting this exponent to a number. You know, these are all just constants out here. So to set the whole thing to a number, you're setting this to some constant as well. And if you solve for the x1 and x2, take my word for it, you get an ellipse. So sometimes you'll hear people talk of an air ellipse. That's the shape of everything in this ellipse is where the probability that the thing will be is less than some number. So you have a 1 sigma ellipse, which says, you know, so much of your probability is within this ellipse. I should have pictures to explain that concept, but I don't. And if it has more than two variables, you get an ellipsoid. In 3 dimensions, you would get an ellipsoid. And you could have more dimensions, but it's still like a hyperellipse. Let's see. The joint PDF of the Gaussian is determined by two variables or two vectors. It's mean vector and its covariance matrix. It's not two vectors. The mean vector and the covariance matrix. I'm not going to go through this. Yeah, uncorrelated implies independent. Of course, the other way always happens, whether it's Gaussian or not. Any linear transformation of a Gaussian yields another Gaussian. And all conditional and marginal PDFs of the individual random variables in a Gaussian random vector are univariate Gaussian. Every single one's a Gaussian. So anyway, kind of quickie Gaussian, multivariate Gaussian. Cover it somewhere.